Hi everyone, welcome to Concept 40. Today we're going to talk about the area of sectors, segments, and annuli. Those three words might be things that you've never heard of before, but that's okay. This is not actually very hard at all. Let's start out with just looking at what a sector is. A sector is simply like a piece of pizza. It is this sort of pizza-sized shape, but it could be the other side. Like the other side could also be a sector. So the angle that is inside this piece of pizza or this sector could be any size. So what I'm saying is that this part is also a sector because you have this angle and it could be that this side is the sector. We're typically going to use this smaller side, but just know that both of those pieces are called sectors. So today we're going to talk about, well, how do you find the area of something like that? Let's think back. This is going to be very related to how we found arc length. So think back to what arc length was. The arc length of a circle is a fraction of the circle's what? It was a fraction of the circle's circumference. And the fraction that you would find is the something divided by something. And it was the arc measure divided by 360. So if you were looking to try to find the arc length of this arc right here, you would want to know, well, what arc measure am I dealing with for this central angle, which is making this arc measure? And this arc length would be whatever that degree was. So say it was a 60-degree angle, you would do 60 divided by 360, which is 1/6 of your circle. So this arc length would be 1/6 of the circle. So likewise, a sector of the circle is not a fraction of the circle's circumference, but it's a fraction of the circle's area. And the fraction is still going to be the same. The fraction of that sector is going to be the arc measure divided by 360. Let's look at a really simple example here. Let's say you have a pizza with a radius of 9 inches. Let's just make a quick sketch over here. So you've got a piece of pizza or a whole pizza, and the radius of your pizza is 9 inches, and the central angle is 40 degrees. So we're looking at a piece of pizza like this with a 40-degree angle. So we're going to see if we can think about how are we going to find the area of this sector. Okay, first question, step 1. What is the area of the whole pizza in terms of pi? So if it has a 9-inch radius, the area, of course, is pi r squared. So you would take that 9 and square it, which you'd get 81. So the whole pizza is 81 pi. That's the whole pizza. Well, what fraction of the pizza is that pizza slice? Well, because it has a 40-degree central angle or a 40-degree arc right here, if you think about, well, what's 40 out of the whole circle, which is 360? We can reduce that. We can reduce 4 and 36, so we get 1/9. So this piece of pizza is 1/9 of my whole circle, of whatever that is. So if we know that the whole pizza had an area of 81 pi, and this one piece of pizza is 1/9 of the pizza, then the area of the pizza slice is 1/9 of my whole area, which was 81 pi. And so I would get 9 pi. So one piece of pizza would have an area of 9 pi. Okay, now that we've talked through all of that, can we write a formula for the area of a sector? Let's think about what we did. We started by finding this fraction. This fraction right here was on the top. What was that 40? That's the arc measure. So we're going to take the arc measure, which I'm going to write as AM, and we always divide that by 360. That's going to give us our fraction. And then instead of multiplying it by circumference like we did for arc length, we're going to multiply that by this part, which is the area of a circle. So it's arc measure over 360 times the area, which is pi r squared. And that is going to give us the sector area. So if you understand arc length, this is very, very similar to that. This is just arc measure over 360 times area, or pi r squared, instead of arc measure over 360 times 2 pi r, which was circumference. So this is very connected to finding the arc length, area of a sector. Okay, the second one we're going to talk about is called a segment. So a segment is the region of a circle that is cut off by a chord. Each time a chord is drawn that is not a diameter, there is a minor segment formed by the minor chord and a major segment formed by the major chord. So let's look at this picture here. Okay, so here's our chord, and on one side we have a minor arc, which is helping us to see this minor segment over here. And then on the other side, we have this major arc. And then inside of that, this whole thing would be the major segment. Now we're going to deal with the minor side of it most of the time. We'll see an example of the major one today. But most of the time it'll be the minor chord, the minor arc and the minor segment that we're looking at. You most of the time won't even hear that language. You'll just hear something like find the area of the shaded segment, and you'll see which one is shaded. But I just wanted you to know that there is a segment on either side of that chord. Okay, so today we're going to be talking about, well, how do you find the area of all of that? So if you basically connect the radii from the center to either end of that chord, you create a sector, right? We have this whole sector that's right here. And we just learned how to find the area of that. So a segment is really a sector. And then you subtract from that, you minus the triangle. Do you see what I'm talking about here? We have this whole sector, in this case, like this big piece of pizza. And then you take away this triangle and you're left with this segment right here. Okay, so let's put this all together and we're going to make a formula. How do you find the area of a sector? Well, see if you can remember this from the last part. It's arc measure over 360 times pi r squared, or area of a circle. How do you find the area of a triangle? Well, that's just 1/2 base times height. So we're going to put that together as our formula. So area of a segment is going to equal, we take the part for the sector, arc measure over 360 times pi r squared, that's the area of a circle, and then we subtract that triangle, or 1/2 BH. All right, and our third new part for today is called an annulus. An annulus is really just like a donut. It's created when you have two concentric circles. So just to show you a couple other examples, you could have a really, really thin annulus, or you could also have a really thick one, more like a donut or a bagel. So the thickness in here could be any size. It can be small and it could be large. Okay, so what two measurements do you need to find the area of an annulus? Well, you're going to need the radius of the outer circle and the area of the inner circle. All right, so if we call one of those radii R1 and the other radii R2, we can put together a formula. It doesn't matter which one's which. So if we take the area of the outer circle as pi R1 squared, and then subtract from that the area of the inner circle as pi R2 squared. I think that formula looks a little funny as long as you understand that these are just subscripts down here. This is probably the easiest one because you're just finding the area of two circles and subtracting to get this inner area. Oh, I meant to shade this in earlier to show that the annulus is this shaded area between the two circles, like a tire or a donut or a bagel. Okay, so let's practice a few. As always, you are welcome to play the video along with me and write down the notes as you go, or you can try these on your own and just check back in to see how you did with these questions. The first two are to find the sectors. So we're going to take our formula, which is arc measure over 360, and we're going to multiply that by the area of the circle, which is pi r squared. So in this problem, we're given both the radius and the arc measure. So we have 60 over 360. We're multiplying that by pi r squared, and our radius is 19, so when I square that, I get 361. When I reduce my fraction, 60 over 360, I can reduce the zeros, and then divide, and I get 1/6. So we need to know what's 1/6 of pi times 361. Well, 6 does not go into 361, and we can't reduce this in any way. So our final answer is 361 pi over 6. That's as reduced as it can go, and this is going to be in meters squared. Okay, the second one, again, we have arc measure over 360 times pi r squared. The arc measure here, this is sort of the larger side. We have the major angle on this side with the major arc. And so we're looking at 225 over 360 times pi, and 16 squared is 256. And surely we can reduce 225 over 360. Let's see, what can we divide by? Well, I know I can divide by 5, and 225 divided by 5 is 45, and 360 divided by 5 is 72. Well, that makes it a little bit easier. Now I can divide by 9. 9 goes into here 5 times, and 9 goes into there 8 times. So my fraction is 5/8. So now I've got 5 times pi times 256 over 8. And I could multiply the 5 and the 256 together, but I think it's going to be easier to divide 256 by 8. 8 goes into here 1 time, and 8 is going to go into there 32 times. So my final answer is 5 times 32, which is 160 pi. And this will be in yards squared. So the area of this sector here is 160 pi yards squared. All right, next we're going to find the area of each of these segments. So remember that to define the segment, we're going to do a sector minus a triangle. That's our basic formula that we're going to follow. And so to find the area of the sector, we're going to start with that fraction. So 60 over 360, I know that's going to be 1/6. Multiplied by the area of the circle, pi r squared. So in this case, it's going to be 100 pi. And then we have to subtract the area of this triangle right here. This is where things get a little bit trickier. Let's think about what kind of triangle this is. If we have a 60-degree angle, and we have 60-degree angle here, and this side is 10, well, this side must also be 10, right? Because this is, these are both radii of the circle, so this must be 10. And let's think about if these are both 10 and this is an isosceles triangle, then this angle and this angle must be the same, right? Because the sides, the angles across from those congruent lengths must be equal. Well, if those two are equal and we have 120 degrees left to work with, then they have to be 60. So that means this whole triangle is equilateral. That is going to be really helpful. Let's make a sketch down here of this triangle so we can see better what's going on. We already know that all the sides are 10. But in order to find the area, we need to find the base and the height. Well, we can call either of these sides the base. So if this is the base, then we're going to need this height. Okay, so again, we have an equilateral triangle making this 60 degrees, and this is 30 degrees. And so hopefully you noticed this from something we did earlier. This is a 30, 60, 90 right triangle. And when we have a 30, 60, 90 right triangle, I can find the side lengths much easier. And so if this side is 10, and then this small side must be 5, which makes my height here 5 radical 3. That's what I need in order to find the area of this triangle. So the area of the triangle, if we go back to our other formula, which is going to be 1/2 base times height, it's going to be 1/2. And the base of this triangle, if we call this the base again, that was 10. And the height of this triangle is right here, which is 5 radical 3. Okay, let's put all of this together. So we have 1/6 of 100. So I have 100 pi over 6. I can reduce that. We can actually make that 50 over 3. So 50 pi over 3. And then on this side, we've got minus 5. I just multiplied those together, times 5 radical 3. Let's keep going. And we've got 50 pi over 3 minus 25 radical 3. And that's as simple as we can get. We can't put these together. One side has a pi, one side has a radical. And this is how your answers are going to often look for segments, because you've got pi in one half of your problem where you're finding the sector, and you might have a radical sometimes in the right hand of the problem for the triangle. So this is my area, and I didn't have a unit on this one, so we could just say square units. I forgot to put a label on that, but that's okay. So it's 50 pi over 3 minus 25 radical 3 square units. All right, our second one. This one is not going to be quite so hard because you can see in the picture we're already given the height of the triangle, so it gives us a lot less work to do. Let's start with the sector. So the arc that we're looking at is this arc right here, the arc measure, and that comes from this central angle, and we know that AOP is 48 degrees, so therefore AOB would be twice that, which is 96 degrees. So we have 96 over 360 times the area of our circle. The area would be pi times 6 squared, or 36. Okay, well, this is nice because 36 and 360 can reduce quite nicely. So we have 96 pi, 36 goes into here 1 time, 36 goes into there 10 times. So we have 96 pi over 10. We can divide everything by 2, and that gives us 48 pi over 5. And that is the area of the sector. Then we need to subtract the area of that triangle. So I'm just going to put it here, minus 1/2 the base times the height. And the height in this case is 4. The base is the one part that we don't know yet, but we can just do a quick Pythagorean theorem to find that. So we have 4 squared plus x squared is going to equal 6 squared. 16 plus x squared is going to equal 36. 36 minus 16, so x squared equals 20. Take the square root of both sides, and x is radical 20, or 2 radical 5. Okay, so back to my formula. We have 1/2 times the base. So we need the base of this whole triangle. And I should have said before, I was just finding the base of one of these sides. So if one side was 2 radical 5, then the total of that's going to be twice that, which is 4 radical 5. So the base will be 4 radical 5 times the height, which is just 4. All right, so combining all of that, we can do 1/2 times 4, that's just 2. And then 2 times this 4 is going to give me 8 radical 5. And we can't combine that any further. It's as fully reduced as it can go. And so our final answer for the area of that segment is 48 pi over 5 minus 8 radical 5. And again, we don't have a unit, so we've just got square units here. All right, last one. Okay, so here's our last one for question 2. We are finding this major segment here. We're going to be finding the shaded area, which is really the major segment. But the easiest way to find this is to just find the area of the minor segment, find this side of it right here, and then subtract from the whole circle when we're done in order to find the other side of it. Okay, so we are going to start with thinking about if we're finding this unshaded part, and we're going to find the arc measure. Well, this is a right angle right here, so that makes my arc measure just 90 degrees. So 90 over 360, we can reduce that to 1/4 multiplied by the area of my circle, which is pi r squared. So it's going to be 64 pi. And then we're going to subtract this triangle, which is just 1/2 times base times height, which is just 8 times 8 in this case, so 64. All right, let's put all this together. 1/4 of 64, that's just 16 pi. And then we're going to subtract half of 64, which is 32. Okay, so that is the final answer for this blue section, for this minor segment, if you will. We want to subtract this now from the whole circle's area so that we can find the shaded part. Well, the whole circle's area, we said, was 64 pi. And we're going to subtract from that, and we need parentheses here. We need 16 pi minus 32 to be in parentheses so that I make sure that this subtraction sign gets sort of distributed through. So it looks like this. We have 64 pi minus 16 pi, And then when that negative comes over to this, it becomes plus 32. Well, 64 pi minus 16 pi, that's 48 pi, and then plus 32. So this is the area, and this is actually has a unit, so it's centimeters squared. That's the area of that gray part, the shaded segment of this circle. All right, we saved the easiest for the last ones. When we're looking for annulus, again, all we're finding here is the area of two different circles and subtracting them. So the radius of our small circle is 12 inches, and the radius of the large circle is 14. So we just need to do pi radius 1 squared minus pi radius 2 squared. So the larger one was 14, so 14 squared is 196. And then the smaller one was 12, so 12 squared is 144. So we have 196 pi, subtract 144 pi. Because they both have pi, we can subtract that. So 196 minus 144 is 52 pi. And that's the final answer. So 52 pi inches squared. All right, number 4. This time we're finding this shaded area, which is sort of like an annulus taking away a sector. Okay, so let's start by finding what that whole annulus is. What's the whole annulus? Well, the radius of the small one is 9 and the large one is 12. So for the annulus, we've got, for the large one was 12, so 144 pi is the area of the large circle, minus the small circle, which is 81 pi. So if we do that math, we get 63 pi is the area of that whole annulus. But we're going to take away this section. And just like for a sector or for an arc length, whatever this section is the same fraction of the annulus as this angle. So if that's a 60-degree angle, 60 out of 360, that's 1/6. This little piece that we're removing is 1/6 of our whole annulus. So we want to subtract 1/6 of it. The other way you could look at it is if we want to take away 1/6, we want to keep 5/6 of it. That's another way you could do it. So we can find what is 5/6 of this, or we could take away 1/6 of that. Let's go ahead with the 5/6 way. So we want to know, well, what is 5/6 of 63 pi? 6 doesn't go into 63, but I can divide by 3. So 3 goes in here 2 times, and 3 goes in here 21 times. So 5 times 21, that gives me 105 pi over 2. That's my final answer. I feel like I did the 60 part pretty quickly. I just wanted to go through back through that, how I found that. 60, it's saying 60 over 360, right? It's arc measure over the 360 to get what fraction is this little part that we want to take out. And so we're taking out 1/6 of it. And that means that 5/6 of it is left. So we could have subtracted 1/6 of 63, or we could have just said, well, what is 5/6 of it? And that's what we did here. So the shaded area here was 105 pi over 2, and this is in millimeters squared. All right, so here we have one where we're going to work backwards. We know the shaded area is 12 pi, and we are going to find the radius. So since this is a sector, let's go ahead and do our sector formula to help us remember that. We have arc measure over 360, that's our fraction, multiplied by pi r squared, which is the area of our circle, and that's going to give us the area of a sector. Okay, so the arc measure is 120, so 120 over 360, that's the fraction, multiplied by we don't know the radius, so we're just going to leave it as pi r squared, and that's going to equal 12 pi. Let's start by reducing this, so 120 over 360, that's just 1/3. Right away I noticed I can get rid of these 2 pi's, so I've got 1/3 r squared, or just r squared over 3, is going to equal 12. Let's multiply by 3 on both sides, so we get r squared equals 36. Take the square root of both sides. So r is radical 36, or r is 6. My radius is 6 centimeters. These questions, when you work backwards or when you're solving for something, sometimes they seem a little bit harder, and so it might be a good idea to just do a quick check by going forward. Like, what if your radius was 6? What would your area be? And go through it that way, and that's just a good way to double check yourself. Okay, Last one, the area of the annulus is 32 pi. We want to find r. We know we are given this length out here, which is the diameter of the bigger circle is 18. That means my bigger radius is 9. So if we just get our formula down of pi r1 squared minus pi r2 squared. And so my bigger radius is 9, we said. So 9 squared, we have 81 pi on the outside. And then on the inside is the one that we don't know. So we're just going to leave this as pi r squared. And this we know the area is 32 pi. Okay, so when you have something like this, where you have these two parts that both have a pi in it, I want you to think back to algebra when we were doing literal equations. And when you had, if you think of pi almost like a variable, we can factor that out as a GCF. We're going to take pi out front as a GCF. So we have pi and then 81 minus r squared. That's going to equal 32 pi. If I divide everything by pi, my pi's go away. So I have 81 minus r squared is going to equal 32. And now we want to get r squared alone. So let's subtract 81 from both sides. That gives me negative r squared equals 49. That's negative. We can multiply both sides by -1 and we get r squared equals 49. And so therefore r is 7 centimeters.